Today we want to add another 2 rules to our list of rules for derivatives. These are situations where we have to have special rules to take some derivative of a combination of functions, that being products and quotients. So let's just jump into the product rule. It's for taking the derivative of a product of functions, say f of x times g of x. So the product rule is for the derivative of a product. The derivative of f of x times g of x is f prime of x times g of x plus f of x times g prime of x. F prime g plus f g prime. The derivative of the first times the second plus the first times the derivative of the second. F prime g plus f g prime. F prime g plus f g prime. That's one way to remember it. The other way is to say f prime g plus g prime f. That might work better for how you remember this. F prime g plus f g prime, or if you want the primes to go first, f prime g plus g prime f. Look for a pattern, a cadence that will help you remember. The derivative of the first times the second plus the first times the derivative of the second. That's the particular incantation that I use for this. The derivative of the first times the second plus the first times the derivative of the second. This is what we need to do to take the derivative of a product of functions. So this goes back to the exercises that we had last week, reading functions for the chain rule. We have to decide how a bunch of functions are combined. Let's do some examples. So here's an example of a product, x cubed times sine x. We see 2 functions, the x cubed and the sine x, and they are being combined with multiplication. So this says we're going to use the product rule. I need to call one of them f and the other one g. So x cubed, that'll be my listed first, so I'll call that f. And I'll say sine of x is g. The other parts I'm going to need are the derivatives of each of these functions. So f prime will be 3x squared And the G prime is cosine x. So my derivative is f prime g, so 3x squared times sine x plus f g prime, x cubed times cosine x. You just want to identify how functions are being combined. Pick one to be f, the other one is going to be g. Any questions? Is the image wobbling a little bit? Okay. I just want to know if I'm the only one that sees that. If you didn't notice it before, now you do, and so I'm sorry, but I don't know if it. Does the projector know that it's hot outside, so it's trying to simulate that? The projector's like, oh man, it's hot outside. I better give it the hot day vibe. It's like, oh, we don't need that. We need to make us think it's cold. Yesterday, I was sitting in my backyard and I was going to do some computer stuff. My computer disagreed with that idea. It's like, oh no, it's too hot. And I go, come on, man, we're sitting in the shade. And the computer's like, oh, fine. And then I like asked it to do something. It's like, fine, just wait. And waited and waited. And I go, all right, all right. And then I touched it up at the top where the little vent is, and I burned my fingers on the case. Like, all right, all right, all right. Then I unplugged it and burned my fingers on the little cord. I'm like, oh, fine, you win. I will shut you off. And stick me in the freezer. No, don't put your computer in the freezer. It's too damp. So we wanted to identify a product when things are multiplied together. We just need to practice this so that it becomes automatic. We don't want to have to think about this. We're going to at the beginning, but we don't want to have to think about this. So if I have x cubed times e to the x, we want to just say the first is going to be x cubed, the second one is an e to the x. So we want to just be able to write down the derivative of the first times the second plus the first times the derivative of the second. That is not how long it should take you to find the derivative of this function. Once we've practiced a lot, that is way too long because I was talking while I was writing it. You should be able to write it faster than anybody can talk to it. If you want to be fancy, notice that both of these terms have a common factor of an e to the x and an x squared. So you might see this derivative when you look it up on the Wolfram alphas with an x squared and an e to the x factored out, leaving a 3 plus x. So I want to warn you of that. Some computer system might give you an algebraic equivalent of your answer. So just make sure that there are some things that are factored, double check before you decide that you're wrong. Either one of these is perfectly acceptable from a learning and practicing standpoint. The first one is preferable because it's a direct application of the product rule. You haven't attempted to do any algebra. Anytime you start doing more algebra steps, you start opening up the opportunity to make mistakes. You don't want to do that. Not at the beginning. Remember that the chain rule is always in effect. The chain rule is always in play. We used the chain rule in the previous two. It's just that the derivative of the inside was 1, so we didn't bother writing it. But in this case, the derivative of the inside on one of these functions is not 1. So we'd say the derivative of the first times the second plus the first times the derivative of the second. The derivative of e to the 5x is e to the 5x times the derivative of the inside, which is 5. I wrote it this way because it looks directly, it came directly from the product rule, and that 5 is out there at the end because I'm just following the format of the chain rule. This is not how we should write this. We shouldn't write our coefficients, our constant coefficients, at the end of our terms. If you wrote this for an answer right now, perfectly acceptable. End of the semester, no, it's no good. You can't be putting your constants at the end. It doesn't matter if it's the same. That's not how we write things. It's not just about right or wrong. It's about fitting in. So one way might be to just put the 5 in front. 5x squared e to the 5x plus 5x cubed e to the 5x. Ideally, you would see that 5 coming, leave a space in front of the x cubed, and put the 5 there when it shows up in the chain rule. Might not happen at the beginning because we're just learning, we're new, and that's okay. Also, we could factor out the x squared e to the 5x just like we did before. And that would leave a 3 plus 5x. Questions? Is that okay? The chain rule is always in play. Pause for copying. I don't read that part. Now it's just a matter of putting functions together that are being multiplied. Well, there's a lot more going on here. This is escalating quickly. So in this problem, we got to think about what we need to do first. We see some e to the x squared. That's some chain rule. The derivative of e to the x squared is e to the x squared times the derivative of x squared, which is 2x. And the derivative of sine of x cubed is cosine of x cubed times the derivative of x cubed, which is 3x squared. But we got to see the overall structure about what's going on here. There are two chain rules combined with a product rule, which is e to the x squared times a sine of x cubed. That's what makes this a product rule. If we think back to the thinking that we applied last week, trying to decide what's the inside and what's the outside, the first thing that happens to x is it gets squared, and then the result is inside the e. So that tells us the inside-outside functions for this factor. But the other thing that happens is this sine of x cubed, right? That these things are separate. So this is not a composition of the e and the sine. It's a product of the e and the sine. So here we're going to say the first is our e to the x squared, and our second sine of x cubed. So g is going to be sine of x cubed. Now to take these derivatives, to get the derivative of the first and the derivative of the second, we're going to need the chain rule. So we take the derivative of e to the x squared. So for f prime, the derivative of e to the x squared is e to the x squared times the derivative of x squared, which is 2x, times the derivative of x, which is 1. So we're done. Okay, we'll always. And then for g prime, the derivative of sine of something is cosine of that thing times the derivative of that thing, which in this case is 3x squared, times the derivative of x, which is 1. We don't write that part. Notice that in this example, I have already graduated to leaving space for the derivative of the inside at the front because it's going to be a monomial. And I want to write that in front of as a coefficient of my exponential or trigonometric functions. This is just style format. If you've written a paper and had to include a bibliography, there's a certain way that you're supposed to list your sources in the bibliography, like the title, author, publisher, year, and that stuff. This is just a style guide. Now I have the 4 parts we're ready to put together using the product rule. The product rule says f prime times g plus f times g prime. I wrote g prime times f because I knew I wanted that 3x squared to go first. If I was really paying attention to what I was doing, I would write it in the same order that I did the previous one. Polynomial, exponential, and then trig function. So we might notice that there are some common factors here. There's an x e to the x squared in common. Maybe we want to factor that out. That'll leave behind a 2 sine x cubed plus 3 times x cosine x cubed. Any questions? Compare that with something like this. Similar elements. I've got sine, I've got a cube, I've got an e to the x squared. That sine cubed by itself doesn't mean anything. That's not a separate factor. That's not taking sine cubed times e to the x squared. This is sine cubed of e to the x squared. So this is not a product rule. You know, it looks like there's 2 separate things. This is because we don't learn properly about parentheses way back in the PEMDAS days. Stupid PEMDAS messing us up even now. If we think about what happens to x here, first it gets squared, then it's the power of e. We take the result, plug it into the sign, then cube the result of that. It's just a chain rule, a bunch of chain rules. So for this one, it's just a bunch of chain rules. The other clue that we just have a bunch of chain rules here, there's only one instance of x. There's only one x that shows up. It can't be a product because I'd have some function of x times another function of x. X would have to appear twice, but x only appears once. So we should be suspicious. It's just a bunch of chain rules. Think about the order of things that happens. Let's see. First, x gets squared. Second, it becomes the power of e. Third, we do the sign of whatever the result is. And fourth, we do a cube. 4 things that happened to x in this order. The chain rule starts off with take the derivative of the outside, which when there's more than one function, that means start at the end. The chain rule goes from the cube down to the square. Remember, the opening lines of the chain rule incantation are take the derivative of the outside with respect to the inside. And since there are 4 lined up, outside is last. So the first thing that we're taking the derivative of is a cube. The derivative of the cube of something is 3 times that thing squared. The derivative of something cubed is 3 something squared times the derivative of that thing. That thing is a sine. That's the next thing on the list. Sine of stuff. The derivative of sine of stuff is cosine of that stuff. So we multiply by the cosine of e to the x squared. The derivative of cosine of e to the x squared, the derivative of sine of e to the x squared is cosine of e to the x squared times the derivative of e to the x squared. The derivative of e to the x squared is e to the x squared times the derivative of x squared, which is a 2x. Big stack of chain rules. If you read the order of operations, start at the outside and work your way in. Any questions? I didn't do any big giant chain rules. This is kind of messy how we wrote it, but we unfortunately didn't leave enough space. And we wrote that 3, but I should combine it with the 2x so my monomials can go first. A better order for this might be 6x e to the x squared times sine squared e to the x squared times cosine of e to the x squared. When the functions start getting weird in calculus and you have to do all these chain rules, this was just chain rule, and there's like multiple chain rules, and I start combining chain rules and product rules and making a big mess of things, that's when the question starts coming up. The most popular question in all math classes at all levels. And that question is, when am I ever going to have to do this? So I will answer that honestly. Never. After you get out of this class, never. If you're about to take some derivatives by hand, you're probably about to get fired unless you're a math teacher. That isn't the point. This is how stuff works. That's the point. That's because it's hot out there. That's how to duck a question 101. That's another important skill to learn as a teacher. Duck questions. Any other questions? So when you find yourself asking the question, when am I ever going to have to know this? Know that that means something. It does mean something. That means you're finally having to work. And you don't want to do it. That's your brain saying, oh boy, this is going to be difficult. And then the subroutine is like, I'll find a way out of it. Because at our core, we're all very lazy and we don't want to expend additional energy. That's how people get killed by like lions and stuff. If you go out there and just play sports ball all day, then you're walking home, you're going to get eaten by a lion because you've used up all of your energy. Like, oh man, I'm so tired. Good game of sports ball, high five. It's like, oh, my thigh's a little bit sore. And then the lion's like, oh, lunchtime. And you're like, oh no. And your friend's like, oh, don't have to outrun the lion, just got to outrun you. And like, oh, I shouldn't have expended all that extra energy. See? So you're naturally going to look for reasons to not do a thing. But if you want to not know how to do math, if you want to not understand math, why are you here? You know what I mean? It's a weird choice to like come here to not know stuff. So doing this later in your career is not the point. I'm not prepping you for your job. If you want training for your job, go get the job and have them train you. I know they won't hire you without a degree, but that's because they want to be gatekeepers. They want to make sure that the right people get college degrees. Does that make sense? And only some of you in here are who they would consider the right people. This is why I want to pay you. Because I want everybody who wants to do this without having to be coerced into it. You know what I mean? Anyway, this is all beside the point. We're going to have to work on our reading skills. So we're going to have to be able to read these and think this way without having to write this down all the time. Because the point of being in a math class is to not have to write down all this friggin' math all the time. Let's talk about the quotient rule. You don't really need, but it's good to have anyway. The quotient rule is, unsurprisingly, for the derivative of a quotient. Isn't it clever how we name things? What should we call the rule for derivatives of quotients? How about the quotient rule? Genius. So this is how differentiation breaks over differentiation breaks over division. You still lead with f prime g, but now you subtract minus fg prime all over is g squared. F prime g minus fg prime over g squared. F prime g minus fg prime over g squared. Yeah. Yes. Yeah, the derivative of the numerator has to go first. It didn't matter in product rule. We could choose whatever we want to be the first and the second, but now we've got a top and a bottom, and there's a subtraction running around, so that matters. Good question. We can't just start messing with it like we could with the product rule. That's why I didn't mess with it in the product rule. F prime G minus F G prime all over G squared. That's not even how you would say this. This is how we're going to remember it though. So we take the derivative of the top times the bottom. So one way that I remember it is thinking of top and bottom, and I say the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. Yikes. Derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. Same kind of thing. You just identify the four parts, plug them into the formula. Being proficient in this is just a matter of time, as with most things in math. You want proficiency, just takes time. When we only have one term in the denominator of a rational function, if we have a monomial denominator in our rational function, it's probably simpler just to make a bunch of terms. But if it's upside down and we don't have a monomial denominator, we can't just split things up. That's not how fractions work. So here is an example of when we would want to use the quotient rule. We have a top. The top is going to be the 3x squared. And the bottom will be 5 minus 2x. We'll need as parts the derivative of the top and the derivative of the bottom. So we take, oops, I need the derivative of the top. So I need the derivative of the top times the bottom minus the top times the derivative of the bottom. All divided by the bottom squared. Yeah, this Wolfram Alpha is very good at this, but to check to see that you're doing it right, you have to be able to do the algebra to make it look like Wolfram Alpha's answer. Because Wolfram Alpha doesn't show its steps. So if you left the problem like this, if I said it gave you a quiz, right now, this is perfectly acceptable. I can see that you decided to use the quotient rule, and I can see that you've plugged all the parts into the quotient rule, and I would be happy with this right now at this point. If you want to simplify it, I would just multiply out the numerator. So I'll have a 30x minus 12x squared plus 6x squared. So in the numerator, we can have a 30x minus 6x squared over 5 minus 2x. I would leave that squared like that. The most important thing to do would not be to see the 5 minus 2x on the top and the 5 minus 2x on the bottom and try to cancel them. Oh, there isn't both sides. Top and bottom, or left and right? Left and right or what? First term, second term. 5 minus 2x is not a factor of the numerator. It's only a factor of this first term of the numerator. There's no 5 minus 2x in this term, so I can't cancel one out. And it doesn't look like I'm going to have a 5 minus 2x in this 30x minus 6x squared. Usually, if that happens, we should have done something at the beginning. If you simplify your fraction, if you get down to here and there's some simplification to do, there's probably some stuff you could have simplified at the very beginning to make your life easier. But don't go back and look for it now. Just put a box and move on. Any questions? All right, tomorrow we're going to practice some product rule, quotient rule, and chain rule. It's just going to be training day. So be ready to read some functions. That's it for today. I'll see you all on tomorrow. Everybody have a good day, and thanks for playing.